In this video, let's do another example of partial fraction decomposition in the case that our rational expression that we're trying to unadd is slightly more complicated. In the previous case, we assumed that all the factors in our denominator were linear. But what if we have a factor in our denominator which is quadratic or cubic? So let's take, for example, 3x plus 1 in the numerator, and in the denominator, let's consider the example of x minus 1 times x squared plus 7. Now once again, I think that if we want to decompose and unadd this fraction, it's reasonable to have two fractions, one with a denominator consisting of x minus 1, and the second with a denominator consisting of x squared plus 7. But the question is, what is reasonable to put in the numerator for a guess of what should go here? In the previous example, when our denominators were both linear, we put constants in the numerator for our guess at the final answer. Now the approach will be similar here, but instead of putting constants as the numerator of both of these functions, I will guess constant as the numerator of the function with a linear denominator. And for a fraction with a quadratic denominator, I will guess that the numerator has a linear format. So here's the general idea. If the denominator has a degree n, say it's quadratic, then guess something of degree n minus 1 for the numerator. If the bottom is linear, degree 1, make the numerator a generic constant, degree 0. If the denominator is quadratic, degree 2, make the numerator a generic linear function, degree 1, and so on. If you had a cubic down below, you would put a quadratic upstairs. Our next move to actually find the values of a, b, and c is to go ahead and to once again clear the fractions. So multiply through by x minus 1, x squared plus 7 equals a times x minus 1 plus bx plus c over x squared plus 7. Multiply all of that by the least common denominator. And as a result, the entire denominator will cancel the entire multiplied LCD on the left. We'll have a x squared plus 7, and we will have the quantity bx plus c times x minus 1. At this point, we can go through and we could multiply everything out. And we could compare the coefficients of x squareds, the number of x's, and the number of constants. Now we will do that in a moment. But we will also do a little trick. And we will try to select a particular value of x that will eliminate all but one of these unknown letters here. Let us, for example, set x equals 1. Let's see what happens if we do this. Set x equals 1 so that I have 3 times 1 plus 1. So that I have a times 1 squared plus 7. So I have b times 1 plus c. So that I have 1 minus 1. And the boon of that trick lies in the back here. 1 minus 1 is 0, which means that 0 will get rid of this entire quantity in the rear. That leaves me just with 4 equals a times 8. b1 plus c times 0 is completely gone. And by subbing in x equals 1 and eliminating this product in the back, I was able to deduce that a must in fact be 4 over 8. A must be 1/2. Alright, now because x minus 1 is the only factor that actually has a root, x squared plus 7 can never equal 0. So this trick can only be used once because x squared plus 7 cannot equal 0. Only x minus 1 could be made equal to 0 and therefore eliminated. So at this point, I will go back into the function and start to distribute things. I now know that a is in fact 1/2. So instead of writing a times x squared, I will go ahead and write 1/2 times x squared. And instead of writing x times 7, I will go ahead and write 7/2. I'll do a distribution in the back as well. Bx times x is bx squared. Bx times -1, c times x, and c times -1. Having done that, let us go through and do some classification of the terms here. Let's categorize them. We have some terms which are quadratic in nature. None appear on the left-hand side. What that implies is that for the quadratic terms, we have 0, no x squareds on the left, equals 1/2 plus b, the number of x squareds on the right. And that tells me that b must be equal to -1/2. Alright, I can also go through and compare the number of x's, for example, that I have on the left. The number of x's on the left is 3. Meanwhile, on the right-hand side, I have -bx's plus cx's. So based on that, it must be true that 3 is equal to -b plus c. At this point, we can use the fact that b is equal to -1/2. So that means if I substitute b equals -1/2 into this equation, I will get 3 equals 1/2 plus c, which means subtracting 1/2 from both sides, we will get 5/2 equals c. We have now figured out the true nature of a, c, and b. So let's go back upstairs and let's make a note that if these are truly going to be equal, the expression on the left and the decomposed expression on the right, then a must be equal to the value that we found of 1/2. b must be equal to the value that we found of -1/2, and c must be equal to the value that we found of 5/2. 3 take away 1/2. And with that, we have unadded, we have decomposed these fractions.